Hello again. I'm here with another example of combined loading. This time, a problem that is a little bit more involved and maybe more practical situation. So what we have here is a sign, which is basically consists of a rectangular plate here, this rectangular plate, and this solid pole with a diameter of 100 millimeters. So the cross section, as you could see here, is circular, and the diameter of this guy is 100 millimeters. Okay, so a sign is subjected to a uniform wind loading of 1.5 kilopascal. So that's 1500 pascal. And what we want to find actually is normal stress and shear stress at point A and point D. So sigma A, sigma D, and tau sub D. Okay? All right, so the first thing we want to do is actually figure out what would be the concentrated load due to this uniform wind loading, which is actually a pressure. So remember, 1500 pascal, pascal means Newton per meter squared. So if you take this, basically this is in a way force per unit area. So if you take this and multiply it by the area of this sign, which is a 1 by 2, that's a 2 meters squared, right? So the pressure times the area, remember pascal is Newton per meter square, so meter square and meter square cancel, so we end up getting 3000 Newton. So now if you put this 3000 Newton right in the center, and then what I did here down here is actually I have really enlarged this section for you, basically this section shown here, not to scale obviously. Remember, this is the section of interest. Again, you have to understand that the more critical section is right here at the base of this post or pole, and because the bending moment is going to be maximum. All right, so right at that section, just move this force, move this 3000 Newton exactly to this location. So that will give me a shear load of 3000 Newtons, right? 3000 Newton meter, right? But when you move this, what would be the effect of this load in terms of moment that is going to generate about these different axes, like x-axis, like y-axis, or like z-axis? So that's what we have to determine. So notice that this load is, this 3000 Newton load due to the wind is parallel to x-axis, right? So it cannot cause any rotation about that axis, but it could rotate about what? Rotate about z-axis, right? And that would be actually your torque. So moment about z-axis is this 3000 times this distance from the z-axis, which is half of the 2 here, right? So that would be your moment about z-axis, or the torque, twisting moment. Now imagine if this load was here, the 3000, what would be the moment of this 3000 about this section here? So that will create what? A moment about y-axis, as shown here in this section. So that would be what? You have 3 meters here, right? And you have another half a meter here because you got to go to the center, right? So that's 3.5. So 3000 times 3.5, and that would be 10,500. So basically what we have done here in this section, we have shown all the internal forces, internal shear and internal moment. But there are 2 moments, one about z-axis, which I called it torque, and one about moment axis. Now notice that, actually before we go and try to find the stresses, notice that this moment about y-axis, what does it do to point A? It's putting point A in tension, so it's pulling on A. But look what happens for point D. So if you had a point here for point C actually, which is the point right here, it will create compression. But we are not looking actually for stresses at that point. But anyways, it would have caused compression, exactly the same load, the same stress rather, but in a compression sense. Okay, but look, point D is sitting on what? On the y-axis. So it's right here, y-axis, this is moment about y-axis. So actually, that's a neutral axis. So the stress sigma at D due to this m sub y is going to be 0. All right, let's go to the next page and try to figure these out. But if you remember that the diameter is 100 millimeters and it's a solid. All right, so what I did, I calculated actually I with respect to the axis. I sub z, which is the moment about, that's the torque, the axis of the torque, actually becomes your j, which is polar moment of inertia that you've seen previously. So that becomes pi over 32. This is changed from 100 millimeters to 0.1 meter, right? So, and remember, I is half of j, or j is twice I, right? And I sub y is only the only other I that we need, because that goes with moment about y-axis. All right, so sigma at A, as you just saw, would be my, m sub y, c. And by the way, you just have to get used to the idea of matching this subscript. If you're using moment about y-axis, you have to use I sub y here. Okay, just plug in. Remember, c is half of the diameter, 0.05 or 50 millimeters. And this is the I. So this comes out to be about 107 megapascal. So that would be the stress here, right here. And by the way, exactly the same one in compression acting at point C here, 107 megapascal. I just mentioned that sigma at D should be 0 since D is on the y-axis, and y-axis then is the neutral axis. Is neutral axis, right? All right, what about shear stress at point A and D? So let me show you what's happening at this point. Let me actually try to erase some of this stuff here. It's getting too messy. All right, so let's look at this. Remember, there is a torque. So actually, this torque, what it does, it creates the same shear stress. Remember, shear stress is maximum on the outside. So this is the TC over J here. And the same TC over J, look at the direction. It's going like this, right? So TC over J here. But so let's go ahead and calculate the TC over J for point A. So TC over J, 3,000, right? Remember, the torque was 3,000, right? Times again C over J. By the way, you could also use 16 torque over pi d cube if you want, because this is a solid shaft. Anyways, but that's the shear stress for both point A and D, but there is a big difference between point A and D. I went the wrong way. Now, we also have the transverse shear here due to this V sub x, right? So what would be the effect of this guy? Again, let me erase some of this stuff here, guys, so I can show you exactly what's going on. So you just saw that due to this torque that we have the TC over J here and TC over J. But what about due to this shear stress? Now, look at this shear. Maybe an easier way would be if I had it like this. If I kind of show this like a circle, look at the top view of this and look at this is your V sub x, right? And point A would be here, and this is point C here actually, and this is point, let's see, D would be over here, for example. Doesn't matter. So now look, so due to this guy, tau at A would be 0, right? Tau at C would be 0, right? Remember this from, a circular section, right? And tau at D would be maximum like this, right? So at A, tau should be 0 due to what? Due to transverse load V sub x. But remember, there is a TC over J here. There is also a TC over J here. But look, I can show you the shear stress is due to this guy. Look, just look at the direction of V sub x and its maximum here. But it's 0 here and 0 here. All right, and then do I add to TC over J my VQ over IT? Yes, because look, the directions are the same. So TC over J and this guy are in the same direction, so you add them to one another. So the question then is, do I use VQ over IT here? So remember, at A, I don't have the VQ over IT, is 0. But at D, I'm going to add it. But no, don't use that. Use the much easier equation, 4 third V over A. So if you do the calculation, this is 15.3, and this is going to come out to be 0.5 roughly megapascal. So this is what I was mentioning to you in the class, guys. I said that the shear stress due to transverse load is much smaller than the shear stress due to twisting. It's very insignificant, and that's why I said usually in design we ignore that. But look, that becomes 15.8. So let's go to the last page, and now I'm going to show you the stress element for this point. So these are the values that I got from the previous page, guys. Sigma at A, which is actually is in the Z direction, and I'm going to talk about these subscripts in a minute. And this is sigma at D, which is 0. And then we got the tau, right? So let me show you here, and how did I come up with this subscript. So you guys remember, due to this M sub Y a minute ago in the, you see how the direction of this sigma is going to be, this 107 megapascal? That's in the Z direction. Remember, this is the Z axis. So that's why I call this sigma Z. So obviously you have the same one down here. But how did I, we could actually show you a three-dimensional element at A, for example. So a three-dimensional element, the stress element would be like this. So you see you got this sigma Z, which is 107 megapascal, right? The same 107 megapascal here, right? But how did I come up with these shear stresses? You see, this is on the Y side, remember, Y side, but acting what? In the Z direction. So that's why I call it tau YZ. But I pressed the pause by mistake, guys. This keeps happening with this iPad. Sorry, guys. But I don't know what I was talking about, but I was just trying to show you that tau YZ and tau ZY are the same thing, and that's how you figure out their, you know, these subscripts. Remember, this is on the, if you look at the center of this cube, you are on the Y side, right? But this is the direction, right? So in the Y side, but acting in the Z direction. And I was just about to say that at point D, you already know sigma at D is 0 and tau YZ is equal to tau ZY, and that was 15.8. That's where actually we added to TC over J, the VQ over IT, or even better than that, 4/3 V over A. I hope this makes sense to you, and you could watch this over and over again. Hopefully, if you have any questions, you can come to the office hour, to the virtual office hour, and ask questions. Again, as always, thank you for watching and listening.